So here we go with lecture number 4. I'm going to go ahead and pop open my PowerPoint slides here for just a second, but I'm going to go through several of the items that we have down here at the bottom that we're going to talk about. Data types and classification. We're mapping features based on attribute values, attributes in our attribute tables for our points, lines, and polygons and rasters. So the first video here we'll talk about data types, and then I'll switch over to the second video for classification. And then the third video for this module is going to be the actual demo itself. A couple of data frames in our MXD that's going to demonstrate some of the items that we're going to talk about here in the lecture. I'm going to minimize this really quick, and I'm going to talk about some maps that we're going to look at later on in the discussion. Some maps that I talked about, and I'll zoom out on those to give you a full context of what we're talking about here. But I'm going to be showing you 3 very similar maps, and already you can see how they're changing. So we'll talk about what the significance of those changes are when we look at them. I've got a demo here that I'm going to get into later on. That'll be a part of video 3. So you can see we have a shapefile here, Baltimore County land use from 2002, and I've got it symbolized 3 different ways. So I'll expand these and work through these as we go on throughout the demo later on, and then we'll see how we can classify data for population using Maryland counties as an example. I'm also going to be using this resource document, the Maryland Land Use Land Cover 2002 classification scheme. It is a resource document listed in your module folder. It is available to you, so you want to have this open as you watch the lecture and as you review the lecture in PDF format. And in case I need to doodle, again, I'm going to have my pseudo whiteboard here in Paint. So I'm going to hop in here and I'm going to start talking about data types to begin, and then we'll talk about classification in the second part of the lecture. So what do we call data types? Well, when I say data types, I'm talking about the type of data contained within the attribute tables of our points, lines, and polygons in our rasters. You'll notice that I have 5 different types, so we're identifying those 5 important types here. But I do have 2 of them underscored. One is nominal data, or descriptive, general descriptive information in our tables, and one is ratio data, which is basically data that is you can do mathematical computations on. So I'm going to focus on those, but I will go through all 5. And so you'll see here in the second bullet that of the 5, the most commonly used are nominal and ratio data. So this is really referring to information contained on pages 68 and 69, 2 pages part of chapter 2, but 2 pages that I think are very important as we move on into learning how to symbolize our maps and work with our data and understand the distribution of our data within our shapefiles and geodatabases. So I did want to pull this out into its own lecture. So we're going to start with nominal data. So we've got qualitative and quantitative data. Of course, quantitative meaning where it has some sort of a numeric value. Whereas here with nominal data, we're talking about qualitative GIS data. So very basically the what and the where. If you think about maybe a point shapefile that represents cities, you may have a column that indicates what the name of the city is, maybe what year it was incorporated, some other code value for that city could be stored in yet a third field. The point of this is that it is exactly what we're saying here. It's descriptive information that is non-mathematical. You can't do any kind of computation on that information, but it does give you that descriptive information that may be useful for labeling in your map or for querying certain types of features. So I have several examples here. You may remember some of these from previous lectures and demonstrations. The Patterson Park tree inventory, for example. We may very simply identified species, and in a species field we identified as maple, oak, or green ash, or something along those lines, using fire hydrants for a fire department application of GIS, whether that fire hydrant or each fire hydrant is in service. If it's not in service, another field may contain information of when that fire hydrant was installed or when it was last serviced. Lines, roads and streams, no different. Again, we're not looking at any kind of mathematical values here, but we're looking strictly at descriptive information. Polygons, land use, land cover, crops, country shapefiles, country feature classes, data that we've worked with already up until this point in exercises and assignments. So again, what you might find in a field is just descriptive information. We'll come back to the land use, land cover discussion here in just a minute. where we will actually use that resource document to look at some of the codes. So speaking of code values, you could have numbers in your database that mean something but are not, again, mathematical values. So instead of saying maple, oak, green ash, hackberry, whatever, we could simply have coded values in the database. And really one of the big things there is for storage on disk, instead of having a 5-character identifier like the word maple in your database, you could have just a 1 that indicates that that is a maple tree, or all of the trees that are labeled as 1 are maples, and that would save a lot of disk a lot of disk space on a network or on a local machine. Now, in an academic environment, working the way we're working, maybe with some of the smaller data sets, it's not as much of a concern, but just understand that some GIS data sets can get kind of large, and it would be good to consider how to use coded values. Roads as line examples, you may classify them into different categories. A1 may be a code that you use for some sort of a major route like a US route or an interstate, versus A2, A3 getting down to more local roads. And again, mentioning polygons here, again using land use land cover as an example, you may have, instead of residential, commercial, industrial, or high, medium, and low density residential areas, you may have polygons that are represented by these individual numbers. You'd have to have some other resource, to indicate what those codes mean, or you could actually have that information included in another field, an actual descriptive information that actually spells out what those different codes mean. But again, that's going to be taking up data space on disk, so you may want to consider that as you're working with this data. So we'll understand what this land use land cover is in just a few minutes, again with our resource document, and what these codes mean specifically here within the state of Maryland, using our state as an example. Really important point here: if you're using some sort of coded value, that you cannot do mathematical calculations, statistics, and that kind of thing. Again, it is just a coded value. It's nominal data. It's some sort of descriptive information. So I've got a couple of screenshots here, and you'll notice that I say land use land cover and see the Maryland land use land cover, or LULC, classification, so that it makes sense what a lot of these numbers mean. So what we'll do is we'll look at these couple of screenshots here, and then I'll just jump out of the document and talk about what I mean for the Maryland land use classification, land use land cover classification. So you'll see that I have a screenshot here from ArcMap. I've got BACO LU02, that's Baltimore County Land Use 02, 2002. And then you can see that I have one checked on that has these different types of land uses, land use and land cover, classified for the entire county in Baltimore County. And then I've got it here again, a third copy. So the first one is just single symbol, and then we've got it symbolized a certain way here with nice descriptors, and then we've got it symbolized a third way here, but instead of having those nice descriptors, we just have the codes sort of all grouped together, and we can see how that's going to change the map. So you can see that in my screenshot I've unchecked this middle of the 3 layers, and I've just checked this bottom one, and you can see how the map has changed. So I'll just kind of toggle back and forth, and you can see how that's breaking out and symbolizing the polygons slightly differently. So if you're familiar with the area, maybe the urban built-up area of Baltimore County surrounding Baltimore City, we have the Reisterstown Corridor, the York Road Corridor, Bel Air Road, Harford Road Corridor, southeastern part of the county, the western part of the county, Catonsville, Arbutus area over here. And of course in the northern parts of the county we don't see as much of that urban built up. We see a lot of agriculture, and we see a lot of forested areas. So again, choosing to symbolize this a different way, here I'm showing low density, medium density, and high density residential in these gradations of yellows into oranges and browns, whereas here I've decided to show them all together and just call them all residential. So the 3 different densities all grouped together. So those polygons are all represented slightly differently. Before I get into ordinal data, I'm going to go ahead and jump into that resource document that I mentioned, because it helps to know what the heck these 11s, 12s, and 13s all mean. So this is the 2002 classification scheme for Maryland land use land cover. This is what's called a modified Anderson classification scheme. Anderson's the name of the gentleman that developed this type of classification scheme back in the 1970s, and so this is Maryland's adopted and adapted version of that same classification scheme. So if you were to click on any of those polygons that I was just looking at in those screenshots, we'll also see those in the demo here in just a little while. Any 10 series number is going to indicate that it is an urban built-up land use, meaning that humans have built it up in some way, that we have some sort of urban activities going on there. So in our 11s, our 12s, and our 13s are our different levels of density of residential. Here we're talking about apartments, condominiums. Here we're talking about maybe duplexes, some row homes, and of course low density residential. We're talking about single family homes with larger lots. As we move on further down in the category, we get into commercial, industrial, institutional, extractive, and 18 urban land. So if we were to combine all of these together, we would basically have a 10 grouping, or a 10 series number grouping of anything that is urban built up. We're going to move into the 20s here, and that is sort of any kind of agricultural activity. So you see the 20 series of numbers, any 21s, 22s, 23s, 24s, and then these 3 series of numbers, and then 25. And I'll talk about these in a little bit more detail here in a second. You're talking about some sort of agricultural operation, whether that's cropland, pasture, orchards, feeding operations. And so to build off of feeding operations, Maryland has decided to break it out into a third digit to break out feeding operations versus agricultural breeding and training facilities. So if you were to see some of these would be very small polygons where they've been interpreted from aerial photography that were specifically tagged as these types of agricultural activities. We move on to the 40s, and you'll notice that there's not a 30 series in Maryland. The 30 series of numbers is rangeland, which we have none in Maryland. Out west, there's a land use land cover code for the 30 series of rangeland, but we don't use that here in Maryland. So if you see polygons that are coded as 41s, they're deciduous forest, 42s is evergreen, 43 is mixed forest. So just again, setting up some context here for looking at those codes. Again, those nominal codes that really mathematically mean nothing. They're just descriptive information that tell us what the different land use land cover is. 50 means any kind of water, and I'll show that to you in the demo. 60 is any kind of wetland, so we may see that excuse me, along any kind of waterways, along maybe along the edge of Baltimore County, along the Chesapeake Bay. Barren land that may not necessarily have any other particular land use that's like a beach or some sort of exposed rock or large outcropping. And then major transportation corridors. If the polygon is big enough, if the area is big enough, sometimes you'll see a transportation corridor like an Interstate 95 will actually be have an entire land use dedicated to it. So this is a great document to have as a resource. I like to use it for a couple of my different demos. So we'll be using this document again in a future module, but I just wanted to use that again as some context for what we're going to be talking about later on. So we've talked about nominal data. We'll also talk about another type of nominal data called ordinal data. So as the first bullet indicates, to place values along a continuum. You're basically ranking the information, but it is still nominal. Even if you give it a number, you are still giving it some sort of a descriptive number that tells you some information about that feature, whether it's a point, line, or polygon. So a couple of examples here, similar to our tree project at Patterson Park. We rated every tree as a 1, 2, 3, 4, or 5. My example here is just 1, 2, or 3, but good, fair, or poor could be the translation for what 1, 2, or 3 is. Again, it's nominal, but it's also ordering the features along some way, in some way, so that you as the user can decide where you want to act, where you want to sort of exercise that decision-making process that we use a GIS for. Similar, low, medium, high-density population or land use. Again, 11s, 12s, or 13s, numerically or mathematically, those numbers mean nothing, but they do correspond to some order where we're going from some sort of value from highest to lowest. Interval data also, as I mentioned before, places data along a continuum, but we have to understand that when you see a value of 0 in a field, you may or may not be dealing with the absence of something. So when it's considered interval data, 0 is arbitrary. So the example that Theobald likes to use is temperature. So if you're reading in your Theobald book, the temperature example is down at the bottom there. The distance between 30 and 40 degrees Fahrenheit and 70 and 80 degrees Fahrenheit is 10 degrees Fahrenheit, but it doesn't make sense to say that one is double or twice as hot as the other. 80 degrees is twice as hot as 40 degrees. And if you think about it, and there's the hint down at the bottom, those same temperature readings in Celsius would not, doubling the low value would not be the same as if you doubled 40 and said that 80 degrees is twice as hot as 40 degrees. It doesn't make sense. Another example of that using temperature is going to be Kelvin, of course, where 0, absolute 0, actually does mean 0. So that's just another way to measure temperature. But in the case of interval data, if you have maybe some sample points of data where temperature is being taken, 0 doesn't necessarily mean that there's a complete absence of heat or molecular motion. Kelvin would be the only scale that uses that. However, 0 degrees on Fahrenheit is does not correspond to the same value as 0 degrees Celsius. Another example, sort of stepping away from Theobald's example, that I like to use in my classes is pH. Everything revolves sort of around the number 7 when you're measuring pH. So if you're doing an environmental science application, you may do some water quality sampling and measure pH. And of course, the higher above you go, 7, towards 14, the more basic it becomes, and the lower the number below 7, the more acidic it becomes. So if you have a sample point where you have a 0 value or a 1 value or a 2 value, I hope that there is no waterway that has such levels of acidity, but we have to understand that those low values or even a 0 value doesn't mean that there is no pH there. It actually would mean that it's a very high acidic value. So pH is another one of those examples where 0 is necessarily, it's not an absence of something or 0 literally taken. It is an arbitrary value along a scale. Where 0 does actually have meaning, or absolute meaning, as I say in the second bullet here, is ratio data. Basically, there is an amount of something. As that third point mentions here, points, lines, or polygons, as you click on them, if you have some sort of a mathematical value in a particular field, you're measuring something. And what I like to talk about in class a lot of times is counts versus amounts. When you talk about counts, you're talking about the number of features in your feature data set. You may have a shapefile with 100 polygons, or you may have a shapefile with 100 points. Your count is 100, but your amount is some measured something at those actual point locations or those polygons or those lines. So examples that I have here at the bottom, you may have a census tract shapefile or a county shapefile that tells you the population of an area. For example, we'll be using Maryland in the demo. We've got 23 counties in Baltimore City, so we have 24 jurisdictions. So that's 24 features, but our population numbers are obviously going to be very different for each one of them. As we were to click on them in ArcMap, we would see that the population of one would be higher than another. So that would be an amount. Area, perimeter, XY locations for points, lines, and polygons. Again, these are all mathematical. These are things that we can actually do computations and statistics on, as I mentioned in the third point there. So area and perimeter, of course, for polygons. Polygons have a perimeter all the way around the edge, and then, of course, they have a calculated area. Lines have length, and, of course, points have XY locations on a Cartesian coordinate system. So these are things that we can actually measure something with, we can do math with. And of course, that's why nominal and ratio data, we consider the two that are most commonly used. Again, using the city as an example, you may have a shapefile that shows cities. You click on the point and it tells you what the name is. The name is Baltimore. That's nominal data. Its population rank in terms of large U.S. cities may be a rank of 3. That's still nominal. Ordinal, it's putting it on some sort of a continuum, but another field may contain the population information for Baltimore City, and that may be 650,000. That's an actual amount of people that live there, so that would be considered ratio data. We'll wrap up here with cyclic data. I do have a website that I've embedded in the slides here for you guys to take a look at. Just an example of an aspect map. I'll probably jump out to Paint here in just a second to sort of draw what I'm talking about. But on page 69, I do like to pull this passage out so that we understand what we mean by cyclic data. And so the example that we use here at the bottom is the average aspect. When you talk about aspect, you're talking about objects' position in the real world, how a building is situated relative to the sun, relative to north, east, south, and west, a mountain range, physical features out in the world, cultural features out in the world, and how they physically sit relative to directions. That was what we mean by aspect. So I'm going to read this passage first, and then I'll maybe sort of diagram it up on the whiteboard, and then I'll go ahead and jump into the Rocky Mountain Wild Aspect Map, and then we'll be done with this portion of the lecture. So if you have your Theobald book with you, page 69, take a look at that second paragraph. The cyclic data type is used to characterize directional attributes such as aspect, degrees on a compass, etc. The reason why this data is different from ratio is that although it does not make sense to compute average aspect, although it does make sense to compute an average aspect, you simply cannot average values. And so what I'll do is I'll jump out here to the whiteboard, and I like to draw this in class. So if you can imagine, maybe I'll just use another tool here to draw a nice perfect circle, because my circles always look bad in class up on screen. So maybe I'll just kind of move that up here a little bit closer. And so if I just draw a line here to kind of make sort of a compass, so give us some compass directions here. And so what Theobald says here on page 69 is that you may have, if we look at, we'll say that this is 0 degrees right here. Pardon my terrible writing on screen. And 360 also happens to be the same north compass direction. And of course down here we're going to have 90. And down here we're going to have 180. Ooh, there goes my 8. And of course we're going to be at 270 over here. That's a big 2. Okay. So what does Theobald say on page 69? Well, although the average of 178 and 182 mathematically is 180 degrees, so let's draw that. Again, this drawing is not going to be to scale here, but what we're saying here, or what Theobald is saying in our example, is that here at 178 and here at 182, mathematically those two numbers will average out to be 180 degrees. So compass direction here, we're talking about south. But if you move on in the example, he talks about that the average aspect of 10, which will be just to the right here of 0 degrees, and then of course 350, mathematically also average out to be 180 degrees, which is south. But if you were averaging direction on a compass, the average direction between 10 degrees and 350 degrees would be due north. So we have to consider that when we talk about cyclic data. So a really good example of cyclic data, or what we call aspect. I'm going to go ahead and clear this out because I'm probably going to use this again later on. The best way to visualize this is looking at an aspect map. So what I'll do here is open up this map, and I'm going to have to sneak it over here from my other slide. And so this is an aspect map. This is a map that the values here are actually being derived from a raster. And so if I were to look at this legend, you could see that we have the different color codes. So if you see a slope, we might have a ridge line right here or right here, and we see red means south, so basically those slopes are facing south, so they would basically have a 180 degree straight south aspect or bearing. If you're looking at the west, northwest, southwest slope, so again here's a ridge line, so we see the oranges, we see the yellows here. We're looking at west facing slopes and south west-facing slopes, excuse me. So we can use this kind of information for doing different types of things. If you can imagine someone wanting to set up maybe solar panels, they want to make sure that at the latitudes at which we live, say here in the United States, we want to make sure we're on south-facing slopes. And so it may not be very beneficial to locate our north and northeast slopes, or maybe a house where we're going to put solar panels. We might want to use this kind of data, some sort of analysis, to place our solar panels on more south, southwest, southeast facing slopes. In the case of, or in the context of this map, we're talking about fire protection districts, and so aspect and also slope of the actual terrain comes into play when considering wildfire protection, especially out in the western parts of the United States, where you have much more extreme topography than maybe what we have here on the east coast of the United States. So again, just an example of how that compass direction comes into play and what we mean by aspect when we talk about these different values. So again, Theobald uses months of the year, January being the first month, December being the 12th month, but they are right next to each other, so they go in cycles, so we call that cyclic data. So what I'm going to do here is I'm going to wrap up. I'm going to close this